Right, let's see. Generally, when it comes to chemistry for JEE or for that matter, NEET also, okay, you will see we will have physical, inorganic, and organic topics. Chapters like mole concept, states of matter, structure of atom, equilibrium, thermodynamics, that all will come around 35 to 40%. Inorganic, which is bonding, blocks, coordination, these are the terms which will come around another 30% in JEE or NEET. Organic, which includes completely carbon, hydrogen bonds, functional groups, etc., that would be around 35 to 40%. This is the broad idea you should have. Okay. And now, mole concept is a part of physical chemistry. And when it comes to mole concept, the first thing you need to understand is the parts of substances. Whenever we have any particular substance, how do we categorize them? We will say substance can be categorized into two forms. One is on the basis of their physical state, and the other thing on the basis of their chemical reactions. So in physical state, we will emphasize whether the substance which you took is a solid, liquid, or a gas. While in chemical equilibrium, chemical reactions, you will look into two aspects, whether it is a pure substance or whether it is in a mixed form. Pure substance include elements, we have molecules and compounds. Mixed substance include multiple molecules, correct? Not just one molecule. You will have in a mixed form. So that means it might have a salt, multiple salts combined that way. Okay. So that is called mixed substance. So you can see substance chemically categorized into pure form or mixed form. Clear? Next. Elements and molecules, all of them are made up of atoms. Okay. And every atom, in a broad perspective, we can say it is categorized mainly into three forms: protons, electrons, and neutrons. Protons are positively charged, electron negatively charged, and neutron are neutrally charged. The basic idea what you need to have about the atom is that atom is more or less an highly concentrated positive charge embed at the center of the atom, and electrons are present across the surface of the hollow space here. Correct. Around this we have a hollow space, so electrons could be found here. Okay. And the center where positive charge lies, that is called as nucleus, and the nucleus contains both protons and neutrons. Clear? This is the basic idea. I'm sure you have it. Now, mole, the term mole is basically a number unit, just like a dozen. Okay, when we use a number unit like dozen means 12, right? 12 entities or 12 quantities. So similarly, mole is a number unit. And the number of entities present in a substance, which is same as the number of carbon atoms present in 1/12 mass of the carbon 12 isotope. So if I take carbon 12 isotope and 1/12 part of its mass, it how many number of carbon atoms which are present in it, that is defined as 1 mole. Okay. And notice, using mass spectrography technology, we are able to predict how many number of particles present in 12 grams of carbon 12 isotopes. And it suggests that we have approximately around 1/12 of mass of carbon 12. If you notice, it is this much amount of mass, 1.66 into 10 raised to the power of 24 this is minus 24 grams. Got it? Now, can I say something here that if at all I say 1.66 into 10 raised to the power of minus 24 grams of carbon mass, this implies one carbon atom. This implies one carbon atom. In that case, if you have a 12 grams of carbon mass, then how many number of carbon atoms it should have? So it is a simple proportion beta. For it's like, if you have 10 rupees and I get one chocolate, and if you have 100 rupees, how many chocolates you will get? This is called a simple proportion. or a direct proportion. So you can see there is a direct proportionality exists here. So I can write this as number of carbon atoms will be equal to 12 grams divided by 1.66 into 10 raised to power of minus 24 grams. Correct? This is how much you should have. Okay.
Yes.
Now, if I take this one, I need to check out 1/12 of this, which is going to be giving you the mole formula. Correct? So one mole will be equal to 1/12 of number of carbon atoms. Correct? 1/12 of number of carbon atoms. So which is equal to 1/12 of 12 divided by 1.66 into 10 raised to power of minus 24. So 12 will get cancelled. And when you solve 1 by 1.66 and all, you will get this as 6.022 into 10 raised to power of 23 carbon atoms. This many carbon atoms you will have. Got it? Is that okay?
Yes.
Right. Okay. Oh, sorry. Here I made a mistake. It should have been 1/12. 1/12 of the mass is this much. Clear? So that means it is of how many number of carbons you will have. So one carbon is equal to 12 times of this one. Got it? So it is 12 times of this is equivalent to one carbon atom. So 12 carbon atoms, 12 grams of carbon atoms includes this 12 multiplied by 12 here. Correct. And that is what we defined it as number of moles, right? So number of moles is how many number of carbon atoms present in this 1/12, which is equal to 6.22 into 10 raised to power of 23 carbons.
So we define mole as number of carbon atoms.
Number of carbon atoms. Okay. In present in how much? In 1/12 mass of carbon 12 isotope.
Okay.
Okay. Mhm. And this is also termed as Avogadro's number. Avogadro's number. So Avogadro's number Na is 6.023, or sometimes you take it as 22 or 23, doesn't make any difference, into 23 entities. So these many entities define Avogadro's number. Okay. Now, I can also write something here that mass of, see, mass of 1 mole of carbon atoms, 1 mole of carbon atoms will be equal to 12 grams, isn't it? Because that's what eventually we got the same thing, right? When you take 12 grams, we got that as 1 mole. Hitansh, is that clear, beta?
Yes, sir.
So this mass, which we are getting, right? Mass of 1 mole of any substance, correct? Is called as the molar mass of the substance. This is
Okay.
termed as molar mass. So from here we get to the definition that molar mass is the mass of a substance, generally in grams, present in 1 mole, 1 mole of a substance. Okay.
Okay.
Now using these terms, whatever we learn, see how the questions can be asked. First thing is find the mass of one carbon atom in grams. Okay. So what I can write here, beta, you know that mass of Na number of carbons that is Avogadro number of carbons, is equivalent to 12 grams, correct? Because Na number of carbons means we have 1 mole of carbons. So then mass of one carbon atom will be equivalent to how much? So that should be equal to how much? 12 divided by Na, correct? These many grams here, isn't it?
Yes.
So you know that mass will be equal to 12 divided by how much is Na value? 6.023 into 10 raised to power of 23, correct? And you also know that this 1 by 6.023 into 23 is nothing but 1.66 into 10 raised to power of minus 24 grams,
Yes.
isn't it? So that will be approximately 1.996 into 10 raised to power of minus 23 grams after multiplication. So that will be the mass of one carbon atom. Is that clear, Bacha? How to relate?
Yes.
Great. Let's go ahead with the next one. What if the question is given like this? Find the 1/12th mass of a carbon atom in grams. So that 1/12th mass of carbon atom. See, can I write this as 1/12th of mass of carbon atom? We just learned that mass of one carbon atom is 12 by Na. Just now we learned. I can write this as 1 by Na in grams. And 1 by Na is 1.66 into 10 raised to power of minus 24 grams. Correct? Now this is where we define a new term beta. That is 1.66 into 10 raised to power of minus 24 grams of an atom of an atom of an atom is defined as 1 AMU. That is atomic mass unit. So for any atom, if you have this much amount of mass associated with it, we call it as, we say that it has 1 AMU mass. Or in the new definition, it is used as 1 U. U is called as unified mass. So in short, 1/12th mass of carbon 12 is 1 AMU.
Okay. Okay.
Check this out. In case if you were asked, convert your mass of 50 kgs into unified mass. If at all I have to convert that into unified mass, then you know that 1 U or 1 unified mass is 1.66 into 10 raised to power of minus 24 grams. Minus 24 grams. What if I write it in kgs? That will be 1.66 into 10 raised to power of minus 27 grams, correct? If you write it in kgs. And that is equal to, I can also write this as 1 by Na grams. Sorry, 1 by Na grams here. If you write it in grams, or 10 raised to power of 3 by Na kgs. And you know that 1 gram from here, right? Can I say that 1 gram from here is always equivalent to Na multiplied by 1 U? So 1 gram of any substance, 1 gram of any substance can be defined as Na multiplied by 1 U. So therefore, if you take 1 gram, which means 10 raised to power of minus 3 kgs of substance, right? So of any substance is equivalent to Na into 1 U. Then 50 kgs, 50 kgs is equivalent to how much amount of unified mass. So therefore, Okay, mass of 50 kg, mass of 50 kg substance is equal to, you know, 50 into Na divided by 10 raised to power of minus 3. That is equal to 50 into 10 raised to power of 3 into Na is 6.022 into 10 raised to power of 23. So that would be equal to approximately 3.011 into 10 raised to power of 28 units or unified mass. So that will be the amount of unified mass. Hitansh, any doubt here?
Avogadro's constant is 6.022 or 6.023.
It's approximately the same, but
Huh.
in generally, as per NCRT, it is given as 6.022. So we usually follow
Okay.
that.
Okay.
But you will not be tested about that value ever, okay? Because
Okay.
in any exam, in any competitive exam, that is the first data they will give. That what you should consider. Should we consider 6.022 or 6.023? Okay.
Okay.
But this part is clear. How to relate grams, how to relate number of moles, how to relate number of atoms, unified mass, AMU. All
So
good?
U is measured in grams,
Correct.
and Avogadro's constant is measured in.
It is a number now. So number
It is a
does not have,
constant.
it's a constant and
Okay.
it is just a number. So that number does not have any units. Okay. It is just a
Okay.
number unit. That's next. Let us understand this term, relative atomic mass. Relative atomic mass is to express mass of a substance or a mass of an atom with respect to 1/12 of carbon 12 mass. Okay. With respect to 1/12 of carbon 12 mass, how much is the relative mass an element or an atom is carrying? Okay. Or from here, we can write the converse also, that mass of a substance or mass of an atom can be always related with its relative atomic mass into 1/12 of this one. So product of relative atomic mass and 1/12 of mass of carbon 12. You know that 1/12 of carbon 12 mass is nothing but 1 AMU. That's what we defined, or 1 U. So, relative atomic mass multiplied by 1 unit or 1 unified mass, that will give you mass of an atom. Okay. So now check it out. Relative atomic mass is dimensionless, and because it is about mass of a substance by 1/12 of it. So it will give you various numbers, which is very, very close to the integer values. In some case, it will be a fraction, but in most cases, it will be a simple integer value. Okay. And this is, you can also regard relative atomic mass as mass number. Also regard this as mass number without units or without dimensions. Okay. For example, mass number of hydrogen is 1. Okay. How do we read this one? Which means it is 1 gram per mole. So if I take 1 mole of a hydrogen gas, I would have 1 gram of hydrogen. Okay. Or I can say it is 1 AMU per atom. Is that making sense?
Okay.
Hmm. So you can see next. If you have helium, helium has 4 AMU per atom. Okay. Lithium has 7 AMU per atom. Beryllium has 9 AMU per atom. Boron has approximately 11 AMU per atom. Nitrogen has 14. Oxygen has 16. Fluorine has 19. Sodium has 23. Magnesium has 24. Aluminium has 27. Right. Next, silicon has 28, phosphorus has 31, okay, sulfur has 32, chlorine has very weird part of it that it will have 35.5. Why it is different, I'll tell you about that. Okay. For argon, it is 40. For potassium, it is 39. Calcium also it is 40. Iron it is 56. Copper, just like earlier, copper we have this as 35.5. Next, zinc. Zinc is 65. Silver, which is around 108. The next, barium. Barium is 137 and iodine is around 127. So please check this out. Of course, bromine also is there. Bromine is 80. That's all okay?
So relative atomic mass is dimensionless, but mass number has dimensions. Gram
Correct.
per mole and atomic mass unit per atom.
Correct.
Okay.
Now notice, find the number of moles in 0.24 grams of carbon. Similarly, find the number of moles of 6022 atoms. Find the mass of 6022 carbon atoms. Okay.
Okay.
And we are all talking about carbon atoms only. So it hasn't been exclusively mentioned here, so you can still check in the question whether we are talking about carbon atom or not. Okay. So let's do it together. What can we write better? 12 grams of carbon contains 1 mole of carbon atoms. Okay. So and if you take 1 gram, so 1 gram of carbon atoms contains.
This is carbon 12 only, no?
Yes, we are talking only default is only carbon 12.
Okay.
1/12 of mole of carbon 12 isotope. Right. Next. In that case, if you have 0.24 grams, so in case if we calculate what is the this much of carbon contains 0.24 into 1 by 12. Now this is 0.02 moles. All okay?
Yes.
From here, can I write these two formulas better? If I have to calculate the number of moles of any species, I can simply write this as what is the mass of that species upon what is the molar mass of that species. Correct?
Okay.
For molar mass, the units are gram per mole. Okay, gram per mole. And for mass, it is only grams. So that's how you will get a mole unit. Hmm. Mole is basically not a unit, but just for our understanding, it is about number of moles what you get. Okay. Next, number of moles of a species can also be written as number of species given. That means how many number of particles we have. that upon the Avogadro's number. That will also give you how many moles it has. Correct? So now you notice that mass of these many number of carbons, correct? These are number of carbons. So number of carbon means I can find out what is the number of moles of carbon. So this is the third part. Number of moles of carbon will be equal to 6022 divided by Avogadro's number, which is 6.022 into 10 raised to the power of 23. So which is equal to 6022 divided by 6022 into 10 raised to the power of 20. I can write that. So that is equal to 10 raised to the power of minus 20 moles. So number of carbon atoms is 10 raised to the power of minus 20 moles. And from there I can write mass is equal to number of moles into molecular weight. The number of moles is 10 raised to the power of minus 20, right? And that into molar mass, which is 12, which is equal to 12 into 10 raised to the power of 20. 10 raised to the power of minus 20 grams. Please check. Any doubt?
No.
Great. Now let us understand one important term in this topic, which is called isotope. See, atoms which are having same number of atoms, which means sorry, same number of atomic numbers, but different number of atomic mass. Now, what are these two terms exactly defined? See, first let me define those terms. Okay, so atomic number is number of protons present in an atom. Present in an atom. Similarly, mass number, that is mass number is number of protons plus number of neutrons. Now, typically, mass atomic number is represented by Z and mass number is represented by A. And to understand that easily, you know, we define something called, notation of an atom. Okay. So if X is the element of any atom, correct, then we write this as, A and Z, like this. This is called the representation or notation of an atom, where A is the mass number, Z is the atomic number. That's clear. So now let me put example. Suppose if the example is H11, H21, H31. So you can notice that where is the mistake happening here. So you notice that the mass number here in both mass number in all three cases are different. Atomic number is same, but the mass number is different. Such cases where the mass number is differing, but the atomic number is same, these are isotopes. And these isotopes have a particular name. So first one is protium. Next, this is called deuterium. And last one, this is called tritium. Okay. See the next one. What is the mass of an atom? Okay. If we say mass of an atom, we add the mass of proton, neutron, electron, correct? Isn't it that what is there in the atom? Of course, there might be other parts of atom also, but more or less in a broad perspective, we have only three major subatomic particles. One is electrons, the other one is protons, then we have neutrons, correct? So mass of an atom is always equal to number of protons into mass of proton plus number of neutrons into mass of neutron plus number of electrons into mass of electron. Can I say that? This will give the total mass, isn't it? Now, what has been noticed, right, Beta? What has been noticed using spectrographic analysis, we learned that the mass of a proton is approximately 1.66, into 10 raised to power of minus 24 grams, while mass of neutron is approximately 1.667 into 10 raised to power of minus 24 grams, while mass of electron is 9.1 into 10 raised to power of minus 27 grams. This is what has been noticed. In fact, mass of proton is 1836 times larger than the mass of electron if you compare these two values. Okay. Now, keeping this information with us, if at all I write the values here and try to figure out what is the mass of an atom, can I say something that this value, that is mass of electron, total mass of electron, will be significantly less than total mass of proton and total mass of neutron together? So in comparison to this value is extremely small value. Got it?
Yes.
So in that case, because this value's contribution is extremely low, and second thing, mass of proton and mass of electron, mass of proton and mass of neutron is almost the same. So we can write it here that mass of proton and mass of neutron is almost the same, and that is approximately 1.66 into 10 raised to power of minus 24, or 1 AMU, isn't it? That is what is 1 AMU is, correct? So mass of proton, mass of neutron is approximately 1 AMU. So can I say that if at all I take this number of that is mass of proton or mass of neutron is common, which is mass of proton common, so that will be mass of proton plus, sorry, number of protons plus number of neutrons, and this part I have ignored. So this is the one which you'll get, and mass of one proton is 1 AMU. So 1 AMU multiplied by what is defined as mass of proton plus mass of neutron, that is nothing but mass number. Hence, mass of an element is always simply its mass number multiplied by 1 AMU. Clear now what is the mass of an atom means?
Okay.
So mass of an atom implies that it is mass number multiplied by 1 AMU. That will give you the actual mass of an atom. That's why I wrote here, for sodium, if the relative atomic mass is 23, and if asked what is the mass of a sodium atom, you can simply write it as 23 into 1 AMU. So 1 AMU is 1 U. So 23 U is the mass of one sodium atom. Likewise, if you have like this here, so how do I read it? See, what can I read it here is mass of one sodium atom, correct, is equal to 23 AMU. Done. This is how you can read it. So if you know the mass number, that means indirectly you know the atomic mass or mass of that particular atom, correct? Likewise, if I tell you that this is the mass of chlorine 3717 is how much? 37 U. Similarly, mass of 3517 chlorine is 35 U, isn't it? This is the mass. Okay. Suppose if I tell you that in atmosphere, if I tell you that in atmosphere, 25% by mole, right? 25% by mole is chlorine 3717 and rest is chlorine 3515. This is the amount of chlorine that is present. Got it? Then what will be the average weight of chlorine? See, average weight of chlorine, right? Average weight of chlorine, which is also called as the mean molar mass of chlorine. Mean molar mass of chlorine will be equal to 37 times 25 plus 35 times 75. This much was the mass divided by, okay, 100, correct? So that makes it how much? This is coming as 35.5, and of course u should be multiplied there, 1 u. So that is equal to 35.5 u. This will be the mean molar mass of chlorine. And that's the reason why molar mass, when you calculate for chlorine, we write it as 35.5. So that half value is not accounted for something like half neutron or half proton, correct? It is accounted on the basis of the averaging of their existence. Itansh, clear beta?
Yes, sir.
Very good. So from here, I can make a general formula that average or mean molar mass. Okay, you can write this. Average, okay, atomic mass. Average atomic mass of an element can be written as A1x1 plus A2x2 plus on so on like this divided by 100. That is equal to summation of AIXI divided by 100. Got it? Now what is this AIXI means? AI means mass number. AI is mass number and Xi is the mole fraction. Xi is the mole fraction. Sorry, percentage mole. Xi is the percentage mole present in it. Clear? Now this percentage mole, the percentage mole of an element, of an element in nature, in nature, how much percentage mole of that element is called as the occurrence or abundance, occurrence or abundance of an isotope. This is the word that is being used. 25% occurrence, 50% abundance, like that. Okay. So you should understand that it is a mole, percentage mole, what we are talking about. Any doubt?
No, sir.
Okay. Now, what if instead of giving it as a percentage mole, what if I give you percentage mass? Okay, let me tell you here. In case of percentage mass given, then what do I do? Notice this carefully. Suppose if I give you x x percentage of, okay, element x with mass number a, sorry, a1 and z, and 100 minus x percentage of mass number a2 and z. These are present, but x is percentage mass now, where x is percentage mass of elements. Okay, in that case, what do we do, better? Because mass is given, you will divide it by the atomic molar mass, correct? Then you'll get number of moles, correct? So therefore, if I consider that there is 100 grams of the total amount, out of which this much amount is for, this isotope, and this much amount is for this isotope, then what is the, you know number of moles, number of moles of, x a1z will be equal to mass is x divided by, okay, mass number is how much, beta? A1, right? Approximately this one, A1 into U. This is the mass number. That's clear?
Okay.
Similarly, if I have to figure out number of moles of x, A2 and Z, that will be equal to x by A2. This is the number of moles. So that gives you total number of moles also. Total moles, right? Sorry, this is 100 minus x. This is 100 minus x, okay? So total moles will be equal to x by A1 plus 100 minus x by A2. Got that? This is the total number of moles. All good?
Yes.
Right. So now, if I take this total mass, total moles, and divide by this one, then what do I get? I will get that as the mole fraction. So that is called mole fraction. So let me put that. Mole fraction of x a1z will be equal to x by a1 into this total. The total, let me call it as capital Y beta. Okay. For our simple understanding, let us put it as capital Y. So this into capital Y, this is the mole fraction, isn't it? Similarly, mole fraction of x, a2 and z, that will be equal to 100 minus x by a2 into y. Got it?
Yes.
Now I got the mole fraction. Now mole fraction multiplied by the molar mass will give you the percentage weight, isn't it? So therefore, average molar mass will be equal to mole fraction. So mole fraction of one particular case, which is x by a1 into y, correct? That into, this is number of moles, mole fraction into how much is the total, how much is the weight of that substance, correct? So how much was the, see, for example, if you have, let's say I said 2 moles of carbon. If at all I have to write the mass of that carbon, what do I do? 2 moles into mass of the carbon is 12 grams per mole, correct? So what you are writing is the mass number only, isn't it? This is the mass number, right? So the same thing I'm going to do it here also, that this into mass number is A1 plus 100 minus x by A2 into y into A2. This will give you the mass. This will give you the average mass of these two. Hitansh, clear beta?
Okay.
So again that A1, A2 are getting cancelled. So what do I get? Basically, I will get x by y plus 100 minus x by y. Isn't it what you are supposed to get? So therefore, that is equal to 100 divided by this y. Y value is what? X by a, a1, x by a1 plus 100 minus x by a2. This is what it is. Clear now? So basically, this is the formula you will be using for average molar mass. Okay. Clear beta? Now, let's see. This is what has been given, that an element has three isotopes. One is 12, 13, 14 mass numbers with an abundance. See, the minute the abundance is given, always please take it in percentage mole, not in percentage mass. Okay. So percentage mole wise, it is 80%, 15%, and 5%. What is the average atomic mass? Please calculate. So I can write average atomic mass is equal to 12 cross 80, 13 cross 15 plus 14 cross 5 upon 100. Is that what you got?
Yes.
So I think this is coming approximately 12.25 if I'm not wrong. Yeah, that's right. Very good. See, what if I tell you the same question is given not with abundance, but it is given as mass percentage? Not what will you do, beta? If it is mass percentage, what will you do? You assume that the total mass is 100. So let me put that as an extra information here, okay? As an alternative question here. So that is alternatively, if the same percentage are mass based, then average atomic mass will be equal to 100 upon, because we are assuming that is the total mass, correct? 100 upon, we need to figure out what is the molar mass, isn't it? So go back to the formula and check out whatever be the percentage that is given, that divided by molar mass, isn't it? So hence, what do we do that? 80 by 12, correct? Plus 15 by 13 plus 5 by 14. This is what we should get. Clear? So let me put that values. 18 divided by 12, which is 6.66. 100 by 6.66. Then 15 by 13, 1.15 plus 5 divided by 14, which is 0.36. Got it? And if I add all of them, 6.66 plus 1.15 plus 0.36, that is coming as 8.17. So 100 divided by 8.17, that is coming as 12.23. See the difference now? That's clear. So there will always be slight difference in the mass there. Okay. See the next one, beta. In case if it is been asked 0.18 grams of aluminium, Al is aluminium. Find number of moles, number of atoms, number of protons, number of neutrons, number of electrons. Now, what you need to know the information, extra information that will be usually given. Given is mass number of aluminium is 27. Okay. Now, which means you should ask that, sir, should we remember the atomic numbers? Unfortunately, 1 to 30 you should better remember. Okay, beta. Of course, you may not remember all at a time right now. Slowly, we will learn into it. Okay. So, could you recall 1 to 10 first?
Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, argon, six,
Sulfur, then
chlorine,
chlorine.
argon, chlorine,
Chlorine,
argon.
very good. So 1 to 18 you are that's good enough. So we'll slowly start recalling, remembering up to 30 also. Okay. Hmm.
Okay.
So that's good. So you can try this out. Will you try it out?
Okay.
Good. So do that. Okay. Let's start with A. A, you got it as number of
Zero
moles,
point.
which is 0.81 upon 27, correct? That is 0.03, right?
Hmm.
Very good. Next, B part, number of atoms. So number of atoms will be equal to number of moles multiplied by Avogadro's number, correct?
Okay.
So which I think you must have got that as 1.0806 into 10 raised to 23 atoms. All good?
Yes.
Very good. C, which is number of protons. Number of protons for aluminum is 13 because atomic number is 13. So
Hmm.
one aluminum has 13, then 0.01 moles will have these many moles of protons. And that moles into Avogadro's number will give you number of protons. Okay. So that I'm getting it as 2.34 into 10 raised to power of 23 protons. These many
13
protons will
into 0.03, no?
0.03. Sorry, 0.03. Yeah. That I'm getting it as 2. Uh, yeah, I'm getting this as, let me calculate again. Yeah, I'll just change it out. So how much I'm getting that into 6.023. Yeah, I'm getting correct only. It's 2.34. Yeah.
Okay.
Next, D. Check out the D part. Number of neutrons. Number of
Same.
neutrons will be number of protons. Sorry, mass number minus number of protons, isn't it? So that in this case will be how many? Number of
Um,
neutrons will be how many?
30 minus 13.
Correct. So 14, right?
Hmm.
So you have 14 neutrons. So therefore, number of neutrons will be equal to 14 into 0.03 into Na. Okay. So 14 into 0.03 into 6.022. So that is coming as 2.53 into 10 raised to power of 23 protons. Number of protons and number of electrons will be same in this case, which is equal to 2.34 into 10 raised to power of 23.
Hmm.
Check.
Yes.
Hmm. Yeah, that's clear.
Yes, sir.
Okay. ठीक. Next one. Try the same thing now, beta, but this time one change. What is that change? Al plus 3. Instead of Al, you have Al plus 3. You got the point? Right. Let's discuss about the numbers again. What was A? What you got? Same thing, right? A is no change. A is
Huh.
0.03 moles.
No change.
B is B is number of atoms, no change.
Hmm.
0.03 into Na, which is 1.806 into 10 raised to the power of 22. No change there. C is number of protons, no change. 2.34 into 10 raised to the power of 23. Okay, one second. Right?
Yes.
Yeah. This is the number of protons. And
Shouldn't B be 1.806 into 10 raised to 23?
8. Why 8?
10 raised to 23.
Yeah. Sorry. This one is 10 raised to 23. Next, D. D is number of neutrons. Even that ain't changing. That is same as the earlier value we got. E is the only part that is changing now, isn't it? Now we have
Yes.
actually 10. So number of electrons are 10 into 0.03. These many moles of electrons into Avogadro's number. So that is 1.806 into 10 raised to power of 23. Correct?
Yes.
This one was 22 correct only but earlier because I am writing it as 1.86, right? Otherwise it will be 0.18. Okay. In the earlier case also it was 10 raised to power of 22 only, not 23. Okay. B was 22. Yeah. Okay. So next. Right. This is the first introductory part of understanding more, right? How it is being related with the elements. Correct. Now, let's try to figure out what is stoichiometry. Got it? And once we know the definitions, again, we'll come back to the mole because we have multiple definitions again laid up there. See, first, measurement of chemicals based on mole ratios in a chemical reaction is all to do with the stoichiometric part. Okay. For example, if you have A plus B giving C plus D. Now, if you see A, B, C, D, these are the stoichiometric coefficients. Correct? These are stoichiometric coefficients. What do you mean by stoichiometric coefficients? That means these are the coefficients which are present across the chemicals. where number of atoms on reactant side and the product side are balanced. Okay. How do we read that? Once you balance it, how do we read it now? This is the way you read it. For A moles of A, we require B moles of B to react and completely form C moles of C and D moles of D. Got it? So the stoichiometric values can be only read in terms of moles, not in terms of mass. I can't say the same thing as A grams of A reacts with B grams of B. That is incorrect. Clear it up? So this ratio proportions are only for moles. And in case of gases, you can do the same thing for volume also. But usually, remember it, it is always for moles. Now, notice first. Generally, when we say molecules, there are two kinds of molecules. One is homoatomic, the other one is heteroatomic. Now, only one type of atom, if it is present, like O2, N2, P4, S8, O3, Cl2, and so on, these are what we call it as homoatomic species. But if you have multiple atoms, which are different atoms, then it is called heteroatomic species, like H2O, NO2, HCl, KClO3, and so on. Got it? Usually, these are also called as compounds. These are also called as compounds. While these are specifically called as molecules only and not compounds. Compounds should be always having a mixed type of atoms. And next term, important term is atomicity, which means number of atoms present in a molecule. Now, atomicity of O3 is 3, P4 is 4, carbon dioxide is 3, C2H6 is 8. That is total number of atoms present in one molecule. That represents the atomicity. That's clear, beta?
Yes, sir.
Now, knowing these terms, you should figure out the next important term known as molecular mass. So basically, when I use the word molecular mass, okay, molecular mass. Molecular mass is same as how we define for the uh, Avogadro number of atoms. Here we are defining it for Avogadro number of molecules. So it is mass of 1 mole of molecule. 1 mole of molecule. Got it? Or you can write this as, mass, total mass of 1 mole of atomic masses of all elements. Whatever the elements that are present in it, that total mass is called as the molar mass. Now here you can see, for example, hydrogen. For hydrogen, we know that atomic mass is 1 U. For chlorine, we learned that as it is 35.5 U. So total how much it is? 36.5 U. That will be the molar mass of HCl. Likewise, if you take H2SO4, it is 2U plus sulfur is 32U plus 4 times of 16U. That makes it 98U. That's clear, beta? This way, could
Yes.
you figure out molar mass of all the compounds given here?
Okay.
Whichever atomic number, if you do atomic mass, if you don't know, you can ask me. Otherwise, just try to calculate and see what is the molar mass you're getting in all cases. Chalo, try this out. Let's see one by one. What is the values you got? H3PO4. How much you got?
98.
98. Very good. Next, H2C2O4.
90.
90. Very good. CH3COOH.
60.
60. Formic acid. Next one.
40.
40. H2O.
18.
18. HNO3.
63.
63. Very good. NaOH,
40.
40. Na2CO3,
106.
106. NaCO3,
84.
84. Yeah. K2CO3,
138.
138. Barium hydroxide,
171.
very good. Aluminium hydroxide,
78.
78. NaCl,
58.5.
very good. KClO3,
122.5.
122.5. KMnO4,
158.
158. FeSO4, ammonium sulfate, 6H2O.
392. 180. 342.
392 or 52?
392. 392, no?
Yeah, 392, then
180.
180 and
342.
342. Correct. Okay. So these are the typical masses. Now, given these kind of compounds, is it, do you know how to uh, use their names, or what is the name, IUPAC name that can be given to them?
Sort of. I don't know the IUPAC name. I know that's a chemical name.
Okay.
Aluminum hide, like that.
For instance, if you have HCl, what do we call it?
Hydrochloric acid.
H2SO4,
Sulfuric acid.
H3PO4,
Phosphoric acid.
H2C2O4.
That I don't know.
Okay. This is oxalic acid. Okay. This is an organic
Uh-huh.
acid which will be using
Oxalic
oxalic
acid.
acid. CH3COOH,
Acetic acid.
acetic acid. HCOOH,
Formic acid.
very good. H2O, water or
Water.
dihydrogen oxygen. Huh? Hmm.
Hmm.
HNO3,
Nitric acid.
right. NaOH,
NaOH is, I don't remember NaOH.
sodium hydroxide. OH is hydroxide always. Okay.
I know it's sodium hydroxide, but I don't know that, like is there any specific name it has?
No, I mean, that way it is called as the soda ash. Okay.
Soda ash.
Hmm. Na2CO3,
Sodium carbonate or washing soda.
very good. NaCO3,
Baking soda, sodium bicarbonate.
very good. K2CO3,
Potassium carbonate.
correct. Barium hydroxide, I mean, that is of
Barium.
course, that is the same thing. Barium hydroxide is
Aluminum.
also called as Bhatia water. Okay. ALOH thrice aluminum hydroxide. NaCl,
NaCl, sodium chloride, common salt.
sodium chloride, common salt. KClO3,
Potassium chlorate.
chlorate, very good. Potassium chlorate. KMnO4,
Potassium permanganate.
very good. The fourth one has a common name known as Mohr salt.
Uh,
MOHR, Mohr salt. Okay.
we got this in our exam last time to calculate percentage of nitrogen in it.
Oh, how did you get there? You had it in your syllabus?
Yeah, we had it last year.
Oh, very good. Next. Next one is glucose. Yeah.
Yes.
The last one is cane sugar or
Sucrose.
simply sugar. Right. See, whatever the compounds which I have written, these are the ones which will be using very, very frequently. Clear, beta? Okay. Now, this is a kind of idea you should have, that in case if you use the terminal, values of these acids or compounds, then you should know all these terms in it. Let me explain for one particular case here. Let's see, I have 0.45 grams of oxalic acid given. Okay. Given any data, the first thing I would suggest is convert everything into number of moles. So 0.45 divided by oxalic acid. Oxalic acid molar mass was 90, right?
Yes.
So, you know that 9 goes how many times? 5 times here, right? So therefore, if I put it as 100, it will be 5 into 10 raised to power of minus 3 moles. Correct?
Yes.
So these many number of moles we have. So let me write on that. So 5 into 10 raised to power of minus 3 moles. Now what is this gram moles means? See, gram molecules. So this is not gram moles, my mistake. Gram atoms, number of gram atoms. Gram atoms. Gram atoms is based on, how many moles we have. For example, if we have these many moles given, right? Clear, beta? So for these many moles, how many gram atoms are present? Gram atom means how many moles of every atom present in it. Okay. So you see, in that, how many atoms are there? 4 plus 2 plus 2. 8 atoms are there. So therefore, it will be 8 times of number of moles given. So 8 into 5 into 10 raised to power of minus 3 gram atoms. If at all I ask you about gram molecule means same as number of moles. How many moles we got? 10 raised 5 into 10 raised to power of minus 3 moles or gram molecules. It's one and the same. Next, number of molecules. Number of molecules means number of moles into Avogadro's number. So 5 into 10 raised to power of minus 3 into Avogadro's number. This one. Clear? So that will be 5 into. I'll write the Avogadro number as approximately 6 into 10 raised to power of 23 into 10 raised to power of minus 3. So that is equal to 3 into 10 raised to power of 21. This many number of molecules. If at all I want to figure out the number of atoms, these number of molecules multiplied by number of atoms in one molecule, which is 8. So that makes it 24 or 2.4 into 10 raised to power of 22 atoms, total atoms present in it. Right, beta? Out of that, if I have to calculate only oxygen atoms, how many oxygen atoms are there? 4. So just multiply 4 instead of that. So 4 into 3 into 10 raised to power of 21. So that makes it 1.2 into 10 raised to power of 22 atoms. Correct? And gram atoms of oxygen. See, 1 mole is equivalent to 1 gram atom. So you have these many moles. So that multiplied by the number of oxygen atoms, which is equal to 4 times. So 4 into 5 into 10 raised to power of minus 3 moles. So that is 20 into 10 raised to power of minus 3 gram atoms of oxygen, or I can write it as 2 into 10 raised to power of minus 2 gram atoms of oxygen. Total number of electrons. See, one atom has how many electrons in here? See, there are total of 4 oxygen atoms, 2 carbon atoms, and 2 hydrogen atoms. So you can see number of electrons will be 2 plus carbon. Each carbon has 6. So 6 plus 6, 12. Plus each oxygen has 8. 8 fours, 32. Correct? So how many do we have here now? 46 electrons we have. So that makes it 46 electrons into 5 into 10 raised to power of minus 3. These many number of total electrons which we have. Okay. So how many neutrons do we have? Hydrogen doesn't have any neutron. Carbon has number of neutrons if you notice. Each carbon has 6. So that makes it 12. Plus each oxygen also has 8. So 4 into 8. Correct. So that means it has 44 number of neutrons. So therefore 44 into 5 into 10 raised to power of minus 3 neutrons. Achha, these are number of moles actually into
So we have
Avogadro's number.
to multiply by.
Yeah, multiply that with Avogadro's number. So that will give you number of electrons or protons. Is this
Also,
factor clear, beta?
how did we get gram atoms of oxygen?
See, the definition of gram atom is this. Suppose if you have the mass number and you're expressing that in grams, that is called gram atoms. Simple. Okay. So just let me put this as a factor here. Okay. Gram atom means
Mhm.
expressing number of moles for, okay, mass number in grams. That's that is what it meant. Same way, gram molecules means expressing number of moles for mass number of molecule in grams. Is that clear, beta?
Okay.
So in short, it is all about moles only. Okay.
Mhm.
Clear?
But even that will have to be multiplied by Avogadro's constant, no?
No, the gram molecule itself means moles. So you have to leave it in moles only.
Okay. Okay.
Okay.
Mhm.
All good.
Yes.